Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that sounds like a simple observation, but hides a profound and mind-bending truth about gravity, energy, and the very fabric of our solar system. The moon always shows us the same face. Think about that for a moment. Every single night, for as long as humanity has gazed upwards, the same craters, the same dark Maria, the same familiar features have greeted us. We never see the far side of the moon from Earth. It remains perpetually hidden, a cosmic secret only revealed by spacecraft. This isn't just a quaint astronomical fact, it's a profound paradox that seems to defy common sense. If the moon is orbiting us, surely it must be rotating to keep different sides visible, right? Or is it simply not spinning at all? If it weren't spinning, imagine what that would look like. It would be like a car driving around a racetrack without its wheels turning, just sliding sideways. Or more accurately, like a person walking around a pole, always facing the same direction in space, which would mean they are rotating relative to the pole. It's a subtle distinction, but it's crucial. The moon does spin, but in such a precise synchronized dance with Earth that it creates the illusion of stillness, a cosmic spotlight perpetually fixed on us. This isn't an accident, it's the signature of immense invisible forces shaping worlds. And understanding why this happens unlocks a deeper appreciation for the elegant, brutal mechanics governing the cosmos. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's start with an observation so fundamental it is almost taken for granted. The moon always presents the same face to Earth. Go outside tonight, look up, and you'll see the familiar pattern of its craters and dark plains. Look again tomorrow night or next week, or even next year, and those same features will be staring back. The man in the moon is always there, always observing us. This isn't just a charming quirk, it is a profound astronomical phenomenon that hints at the powerful invisible forces at play between celestial bodies. The immediate intuitive thought might be, well, if it always shows the same face, it must not be spinning at all. But here's where physics gets genuinely strange. Because the truth is far more complex and far more fascinating. The moon is spinning. It's just doing so in a way that perfectly, exquisitely synchronizes with its orbital journey around our planet, creating an illusion of stillness that has captivated thinkers for millennia. To truly understand this cosmic ballet, we first need to get precise about what we mean by spinning and orbiting. Imagine yourself standing in the middle of a large room. Now imagine a friend walking in a perfect circle around you. If your friend never turned their body, always facing the same wall as they walked, you would see all sides of them as they completed their circle. This is what we call revolution, moving around a central point without rotation, spinning on an internal axis. However, if your friend, while walking in that circle around you, always kept their face pointed towards you, you would only ever see their front. From your perspective, their face would be fixed. But for your friend to achieve this, they would have to be constantly turning their body, rotating on their own axis as they revolve around you. That turning, that rotation is what we're talking about. The moon does precisely this. It rotates on its own axis exactly once for every single orbit it completes around the Earth. Let's put some numbers to this. The moon takes approximately 27.3 Earth days to complete one full orbit around our planet. This is its sidereal orbital period. And here's the kicker. It also takes approximately 27.3 Earth days to complete one full rotation on its own axis. Because these two periods are precisely matched, the same side of the moon is always facing us. If the moon didn't rotate at all, meaning it kept one specific side perpetually facing a fixed point in space, say a distant star, then as it orbited Earth, we would eventually see all of its surfaces. Imagine that friend again, walking around you, but this time they are truly not rotating though. Their face is always pointing towards, say, the north wall. As they walk around you, you would see their front, then their side, then their back, and finally their other side before seeing their front again. The fact that we don't see the moon's far side proves it is rotating. It's just rotating at the perfect rate to keep one face locked on Earth. This phenomenon is known as tidal locking, and it's far more common in the universe than you might think. But why this perfect synchronicity? Why isn't the moon spinning faster, or slower, or randomly? The answer lies in the subtle yet immensely powerful gravitational interactions between the Earth and the moon. We often think of gravity as a simple force pulling two objects together, like a single invisible string. But gravity is far more nuanced than that. It's a force that depends on distance, specifically the inverse square of the distance. This means that the side of the moon closer to Earth feels a stronger gravitational pull than the side of the moon farther away from Earth. This difference in gravitational pull across the body of the moon is absolutely crucial. It's what we call a differential gravitational force, and it's the engine behind tidal locking. The moon isn't a perfectly rigid spherical billiard ball. It's a somewhat deformable body, and the Earth's gravity doesn't pull on it as a single point mass. Instead, the Earth's gravity subtly stretches the moon. The part of the moon closest to Earth gets pulled a little harder, and this part farthest away gets pulled a little less, causing the moon to bulge slightly along the line connecting it to Earth. This creates what are known as tidal bulges on the moon itself, two slight elongations, one facing Earth and one on the opposite side. Even though the moon is solid rock, these bulges exist, a testament to the immense power of gravity over cosmic timescales. Now imagine the moon in its early history, perhaps spinning much faster than it does today. As it spun, these gravitational bulges would not always be perfectly aligned with the Earth. If the moon was rotating faster than its orbital period, these bulges would be slightly ahead of the direct line between the moon and Earth. The Earth's gravity would then exert a torque on these misaligned bulges. Think of it like this. If you have a dumbbell and you're trying to spin it, but someone is gently pulling on one end more than the other, that pulling force will try to slow down or speed up the dumbbell's spin to get it to align with the direction of the pull. In the moon's case, the Earth's stronger pull on the closer bulge and slightly weaker pull on the farther bulge would try to drag those bulges back into alignment along the Earth-Moon axis. This gravitational tug-of-war acts like a cosmic brake. This braking effect isn't some gentle caress. It's a relentless, persistent force that has been at work for billions of years. The differential gravity of the Earth exerts a torque on the moon's tidal bulges, constantly attempting to pull them back into alignment with the Earth-Moon axis. If the moon was spinning faster than its orbit, this torque would act to slow its rotation. If it was spinning slower, the torque would act to speed it up, though this is less common in initial conditions. The energy dissipated by this braking action doesn't just vanish, it's converted into heat within the moon's interior, causing slight internal friction and deformation. Over vast spans of time, this process of energy dissipation and torque application gradually slowed the moon's rotation until it reached a stable equilibrium. That equilibrium is tidal locking, the state where the moon's rotational period perfectly matches its orbital period. Once this synchronous state is achieved, the tidal bulges are permanently aligned along the Earth-Moon axis. When they are perfectly aligned, the gravitational torque from Earth on those bulges effectively vanishes. There's no longer any force trying to speed up or slow down the moon's rotation relative to its orbit. It's like a perfectly balanced top that has found its stable, quiet spin. This isn't just a fascinating curiosity, it's a fundamental process that shapes planetary systems across the universe. It's why many of the large moons of Jupiter and Saturn, like Io, Europa and Titan, are also tidally locked to their massive parent planets. It's a testament to gravity's power to not just pull things together, but to sculpt their very motion and orientation over cosmic timescales. We've now seen how the Earth's immense gravitational pull, specifically its differential effect across the moon's body, acted as a cosmic brake, slowing the moon's initial rotation until it became tidally locked, forever presenting the same face to our planet. But this isn't a one-way street. Newton's third law tells us that for every action there is an equal and opposite reaction. If the Earth's gravity is tugging on the moon, then the moon's gravity must also be tugging on the Earth. If the moon can raise tidal bulges on itself, can it do the same to our planet? And if so, what are the implications for Earth's own rotation, its oceans, and even the length of our day? That question leads us directly to the next chapter, where we'll explore the great slowdown, how the moon is stealing Earth's day and making tides, and uncover the reciprocal, astonishing effects the moon has had and continues to have on our homeworld. Last time we unraveled the cosmic secret of why the moon always shows us its familiar face, a profound truth rooted in the elegant, brutal mechanics of tidal locking. We saw how Earth's immense gravity acted as a cosmic brake, slowing the moon's rotation until it spun in perfect synchronicity with its orbit. But here's the mind-bending twist, the reciprocal dance that truly elevates this into a gravitational ballet. If Earth's gravity has such a powerful transformative effect on the moon, what about the moon's gravitational embrace on our planet? What are the moon's effects on Earth, particularly concerning its rotation, our oceans, and the very length of our day? Prepare yourselves, because the answer is just as astonishing, and it's happening right now, shaping our world in ways you might not even realize. Let's start with the most visible, tangible evidence of the moon's gravitational pull on Earth, the tides. You know them, you've seen them, the rhythmic rise and fall of the oceans. But have you ever truly paused to consider what causes them? It's not just that the moon pulling water towards it like a magnet. Oh no, it's far more nuanced, far more fascinating. That. Imagine our Earth, a magnificent sphere mostly covered in water spinning through space. The moon, our loyal companion, orbits us, constantly exerting its gravitational influence. Now gravity, as we know, isn't a uniform force across a large body. It weakens with desistance. This is absolutely key. The side of Earth closest to the moon experiences a stronger gravitational pull than the centre of Earth, and the side farthest from the moon experiences an even weaker pull. This difference in gravitational force across Earth's body is what we call a tidal force. Think of it like this: the moon is trying to stretch Earth. It pulls harder on the near side, creating a bulge of water that rises towards it. Simple enough, right? But what about the other side of Earth, the side away from the moon? This is where it gets genuinely strange and often counterintuitive. On that far side, the moon's gravity is weakest. The moon is pulling the centre of Earth away from the water on the far side, leaving that water to bulge outwards in the opposite direction. So we end up with two high tides at any given moment, one on the side of Earth facing the moon and another on the side directly opposite. And in between these bulges, the water levels drop, creating two low tides. This is why most coastal areas experience two high tides and two low tides approximately every 24 hours and 50 minutes, the extra 50 minutes being the time it takes for the Earth to catch up to the moon in its orbit. It's a beautifully choreographed dance, a constant stretching and relaxing of our planet's watery skin. Of course, the sun also plays a role in our tides, though its effect is about half that of the moon's due to its much greater distance. When the sun, earth and moon align during new and full moons, their gravitational pulls combine, creating extra high spring tides. When they are at right angles during quarter moons, their pulls partially cancel out, resulting in weaker neap tides. But make no mistake, the moon is the primary conductor of this oceanic symphony. But here's where the story deepens, moving beyond the visible ebb and flow of our seas. These tidal forces don't just affect the water, they affect the entire Earth. Our planet isn't a rigid, unyielding sphere. It's a dynamic, slightly elastic body, and the moon's gravity stretches the solid Earth itself, creating like solid Earth tides. These are much smaller than ocean tides, only about 20-30 centimetres, but they are absolutely crucial to understanding the moon's profound impact on our planet's rotation. Now remember how Earth's gravity created tidal bulges on the moon, and how the moon's rotation tried to carry those bulges ahead of the direct line to Earth? Ahead of the S. And how Earth's gravity then pulled back on those leading bulges, slowing the moon down. Well, the exact same principle is at play here, only in reverse. Earth is spinning much faster than the moon orbits us. Our day is roughly 4 hours, while the moon's orbital period is about a couple of days. As Earth rapidly rotates, it tries to carry its own tidal bulges, both the oceanic and the solid body ones, ahead of the direct line connecting Earth's centre to the moon. Imagine the moon like a cosmic spotlight trying to hold those bulges in place, but Earth's spin keeps trying to drag them forward. What happens next is pure elegant physics. The moon's gravity exerts a subtle but persistent pull on these leading bulges. It's like a tiny invisible hand reaching out and tugging backwards on the bulge that's trying to get ahead. This continuous tug creates a torque, a rotational force that acts as a constant gentle brake on Earth's rotation. This is what we call tidal friction. As Earth spins through these bulges, there's friction between the moving water and the seabed within the solid Earth itself. This friction dissipates energy, converting the rotational energy of our planet into heat. And the direct consequence? Earth's rotation is gradually, imperceptibly slowing down. Think about that for a moment. The moon, our serene, unchanging companion, is actively slowing down the spin of our entire planet. This isn't just a theoretical idea, it's a measurable phenomenon. The length of our day is not constant, it's getting longer. How much longer? The longer yet. A tiny amount, about 1.8 milliseconds per century. That might sound incredibly small, almost negligible. But over geological timescales, over billions of years, these milliseconds add up to truly astonishing effects. If Earth's rotation is slowing down, where does that lost angular momentum go? This is where the cosmic ballet gets even more intricate, demonstrating one of the most fundamental laws of the universe, the conservation of angular momentum. In a closed system like the Earth-Moon duo, angular momentum must be conserved. If Earth loses it, something else must gain it. And that something else is the moon. As Earth's spin slows, the angular momentum isn't destroyed, it's transferred to the moon. This transfer of energy doesn't make the moon spin faster, it's already tidally locked, remember, but it gives the moon a tiny energetic push outwards. This push causes the moon to gradually, inexorably recede from Earth. Yes, you heard that right. Our moon is slowly but surely drifting away from us. How fast? About 3.8 centimeters, or about 1.5 inches per year. Think of it. Every year the moon moves about the length of your thumb further away from Earth. This isn't mere speculation. We have direct evidence! The Apollo missions left retroreflectors on the moon, allowing us to bounce lasers off them and precisely measure the Earth-Moon distance. These measurements confirm the recession rate. Furthermore, paleontological evidence, like the growth rings in ancient corals, shows that days were shorter and years had more days hundreds of millions of years ago. For example, 400 million years ago, a day on Earth was only about 22 hours long and a year had roughly 400 days. This perfectly aligns with the predicted slowing of Earth's rotation and the moon's recession. It's a truly profound and mind-bending truth. The very forces that lock the moon's rotation to its orbit are simultaneously lengthening our days and pushing our celestial partner further into the cosmos. What does this mean for the future of our Earth-Moon system? The dance continues, but the steps are changing. Our days will continue to get longer, and the moon will continue to drift away. This process will continue for billions of years. Eventually, far, far into the future, a new equilibrium will be reached. Just as the moon became tidally locked to Earth, Earth too will eventually become tidally locked to the moon. When that happens, Earth's rotation period will match the moon's orbital period. Our day will be incredibly long, around 47 current Earth days. And just like the soon Earth will always show the same face to the moon. Imagine that, one side of Earth perpetually gazing at the moon while the other side never sees it. Don't worry though, this cosmic embrace won't happen for another 50 billion years or so, long after our sun has expanded into a red giant and consumed Earth. So we won't be around to witness that ultimate synchronization. But the thought itself is a testament to the astonishing long-term power of gravity and tidal forces. So the moon doesn't appear to spin from our perspective because it is a tidal socked, a state achieved by Earth's gravity slowing its rotation. And in return, the moon's gravity is slowing Earth's rotation, lengthening our days, and pushing itself further away. It's an elegant, brutal, and incredibly dynamic gravitational tug-of-war, a cosmic feedback loop that has shaped both our worlds for billions of years and continues to do so. We often look up at the moon and see a stable, unchanging presence. But beneath that serene facade lies a story of constant motion, immense forces, and a profound interconnectedness that literally stretches across space and time. It's a powerful reminder that nothing in the universe is truly static, and even the most familiar celestial bodies are part of an ongoing, intricate cosmic ballet. What are your thoughts on this incredible interplay? Does it change how you look at the moon? Drop a comment below and let us know. Next time we'll dive even deeper into the mysteries of tidal locking, exploring other worlds in our solar system where this phenomenon plays an even more dramatic role. We'll meet moons that are being stretched and squeezed, volcanically active worlds, and perhaps even discover what happens when tidal forces get too intense. Join us as we continue our journey into the fascinating world of scientific wonder. Welcome back, cosmic explorers, to Dreamy Science. In our last chapter, we delved into the elegant, brutal mechanics of how Earth's gravity has slowed the moon to its tidally locked state, and how the moon, in turn, is gradually breaking our own planet's spin, sending itself ever so slowly spiraling away. We even touched upon the distant future, billions of years from now, when Earth itself might become tidally locked to the moon, presenting one face perpetually to its celestial dance partner. But here's a profound and mind-bending truth. The gravitational ballet we've been exploring isn't unique to our little corner of the solar system. Oh no, this cosmic dance of tidal forces, this subtle yet immensely powerful sculpture of worlds, plays out across the entire universe. Tidal locking isn't just a quirk of our moon, it's a fundamental and widespread phenomenon, shaping planets and moons in ways that are often far more dramatic and extreme than what we experience here at home. So buckle up, because today we're embarking on a grand tour of our solar system, venturing beyond our familiar Earth-Moon system to witness the astonishing effects of tidal locking on other worlds. We're going to see how intense gravitational tugs can create geological infernos, carve out hidden oceans, and even lock entire planetary pairs into an eternal face-off. Let's start our journey close to home, yet worlds away in terms of its unique tidal situation, the innermost planet, Mercury. For a long time, astronomers believed Mercury was completely tidally locked to the Sun, always showing the same face, just like our moon to Earth. It made sense, right? Is the closest planet to our star feeling the Sun's immense gravitational pull more intensely than any other world? If our moon is tidally locked to Earth, surely Mercury must be to the Sun. But space probes like Mariner 10 and Messenger revealed a genuinely strange truth. Mercury isn't tidally locked in a 1:1 ratio. Instead, it's locked in a 3:2 spin-orbit resonance. What does that mean? It means that for every 2 times Mercury orbits the Sun, it rotates exactly 3 times on its own axis. Imagine that! Its day, from one sunrise to the next, is actually longer than its year. A single solar day on Mercury lasts about 56 Earth days, while its orbital period, its year, is only about 88 Earth days. This isn't just a cosmic coincidence. It's another elegant, brutal consequence of tidal forces, specifically amplified by Mercury's highly elliptical orbit. When Mercury swings closest to the Sun, a point called perihelion, the Sun's tidal forces are at their strongest. At this point, the gravitational pull acts most effectively to lock Mercury's rotation to its orbital motion. Because of the eccentricity of its orbit, the planet doesn't quite settle into a perfect 1-1-1 lock. Instead, the tidal forces nudge its spin into this stable 3-2 resonance, a kind of gravitational sweet spot where the tidal torques average out over its eccentric orbit. Think about what this means for an observer on Mercury. If you were standing on its surface watching the Sun, the experience would be bizarre. The Sun would rise, slowly traverse the sky, then briefly reverse course before continuing its journey, only to set again, taking to Mercury years to complete one full cycle. This phenomenon's a direct, mesmerizing testament to the Sun's powerful tidal embrace, twisting and shaping Mercury's rotation into a pattern that is both stable and utterly alien to our earthbound experience. The sheer intensity of the Sun's gravity, even at its weakest points in Mercury's orbit, is enough to maintain this peculiar dance. Now, let's journey further out, past the inner planets, to the realm of the gas giants, where tidal forces truly unleash their most spectacular and destructive power. Our first stop, Jupiter, the king of planets, and its 4 largest moons, the Galilean satellites Io, Europa, Ganymede, and Callisto. Here's a fascinating fact. All 4 of these magnificent moons are tidally locked to Jupiter, just like our moon is to Earth. They each perpetually show the same face to the giant planet. But the story doesn't end there, especially not for Io, the innermost of the Galilean moons. Io is arguably the most volcanically active body in the entire solar system. Its surface is a vibrant, ever-changing canvas of yellow, orange, and red, constantly being repaved by hundreds of active volcanoes spewing sulfur and silicate rock. This isn't ancient geology. We're talking about eruptions that are happening right now, powerful enough to blast plumes hundreds of kilometers into... What fuels this? Vernon. You guessed it, incredibly intense tidal forces. But it's not just Jupiter's direct pull. Io is locked in a complex gravitational dance with its 2 closest siblings, Europa and Ganymede, thanks to a phenomenon called orbital resonance. For every 1 orbit Ganymede completes, Europa completes 2 and Io completes 4. This rhythmic alignment means that Io gets a gravitational tug from Europa and Ganymede at predictable intervals, preventing its orbit around Jupiter from becoming perfectly circular. Instead, Io's orbit is slightly elliptical. And here's where the magic, or rather the brutal physics, happens. As Io swings closer to Jupiter, it feels a stronger gravitational pull stretching it into a more elongated shape. As it moves further away, the pull weakens and Io relaxes, becoming more spherical. This constant rhythmic stretching and squeezing, this relentless tidal kneading from Jupiter and its fellow moons, generates immense friction deep within Io's interior. Imagine bending a paperclip back and forth rapidly. It quickly becomes hot to the touch. Io is experiencing this on a planetary scale, generating enough internal heat to keep its entire mantle molten and drive its astonishing volcanic activity. It's a dramatic, fiery testament to the power of gravitational forces, turning a moon into a living, breathing, erupting world. Moving outward from Io, we encounter Europa, another of Jupiter's Galilean moons. Like Io, Europa is tidally locked to Jupiter and experiences tidal heating. While not as extreme as Io's volcanic frenzy, Europa's tidal kneading is believed to be just enough to maintain a vast salty ocean hidden beneath its icy shell. This subsurface ocean, kept liquid by the warmth generated by gravitational friction, is considered one of the most promising places in our solar system to search for extraterrestrial life. Here, tidal forces aren't just destructive, they are potentially life-sustaining, creating a warm, dynamic environment far from the Sun's direct influence. Our journey continues to Saturn, a ringed jewel of the outer solar system, and one of its smaller yet incredibly intriguing moons. Enceladus. Like Europa, Enceladus is tidally locked to its giant parent planet. And like Europa, it harbours a global subsurface ocean kept warm by tidal heating from Saturn. But Enceladus takes it a step further. From deep fissures near its south pole, nicknamed tiger stripes, massive geysers continuously erupt, blasting plumes of water vapour and ice particles hundreds of kilometres into space. These plumes, directly observed by the Cassini spacecraft, are a direct consequence of Saturn's tidal forces warming the Moon's interior, causing the water to erupt through cracks in its icy shell. Enceladus is literally spraying its tidally heated ocean out into space, offering us a direct sample of its potentially habitable environment. From the fiery depths of Io to the hidden oceans of Europa and the icy geysers of Enceladus, we see how tidal locking isn't just about a moon showing one face. It's about a dynamic, energetic interaction that can profoundly reshape a celestial body, driving its geology, influencing its potential for life, and creating some of the most spectacular phenomena in the solar system. But what if two bodies are so evenly matched, so perfectly entangled in their gravitational embrace, that they both become tidally locked to each other? For this unique scenario, we must travel to the distant icy reaches of our solar system, to the dwarf planet Pluto and its largest moon, Charon. Pluto and Charon are a marvel of mutual tidal locking. They are so close in size, Charon is about half the diameter of Pluto, and so gravitationally intertwined that they have both become tidally locked to one another. This means that as Charon orbits Pluto, it always shows the same face to Pluto. And simultaneously, Pluto always shows the same face to Charon. Imagine two dancers perpetually facing each other, spinning around a common point in space, never breaking eye contact. That's Pluto and Charon. Their combined system acts almost like a double planet orbiting a barycenter, their common centre of mass that lies between them rather than inside Pluto itself. This extreme mutual tidal locking is the ultimate expression of gravitational synchronicity, a cosmic embrace where neither body dominates the other entirely, but rather they settle into a shared, stable, and truly unique dance. It's a testament to how tidal forces can equalize and synchronize the rotations of celestial partners over vast spans of cosmic time. So, from the 3-2 resonance of Mercury under the Sun's intense gaze, to the volcanic fury of Io, the hidden oceans of Europa and Enceladus, and the perfectly synchronized ballet of Pluto and Charon, we witness the pervasive and powerful hand of tidal locking. It's a fundamental force, a cosmic sculptor that dictates the spin, heat, and even the potential for life on worlds across our solar system. These aren't just isolated curiosities, they are profound examples of how gravity, in its most subtle yet relentless form, shapes the very fabric of planetary systems. The story of tidal locking, this gravitational tug-of-war, is far from over. It's a constant ongoing process that continues to reshape our universe. We've seen its effects within our solar system, but what about beyond? What about planets orbiting other stars, or moons orbiting gas giants in alien systems? The possibilities and the extremes are truly mind-boggling. Next time, we'll cast our gaze even wider, venturing beyond our solar system to explore the truly bizarre and extreme manifestations of tidal forces on exoplanets. We'll discover worlds where one side is perpetually baked and the other perpetually frozen, where wind speeds are unimaginable and where life, if it exists, must adapt to conditions far stranger than anything we've encountered so far. The universe, as always, has more secrets to reveal, and we're just getting started. If you're enjoying this cosmic journey, drop a comment below and let us know what you find most fascinating about tidal locking. We've journeyed across our own cosmic neighbourhood, discovering the profound, elegant mechanics of tidal locking, from our familiar moon to the volcanic heart of Io, the icy depths of Europa and Enceladus, and the mutual embrace of Pluto and Charon. These are truly astonishing phenomena, right? But what if we told you that these examples are just the beginning? that the universe holds even more dramatic, mind-bending manifestations of tidal forces shaping entire worlds in ways that stretch our imaginations to their very limit. Strap in, because now we're casting our gaze beyond our solar system to the vast teeming cosmos of exoplanets. Here, the story of tidal locking becomes even more extreme or alien, and in some cases surprisingly even more hopeful for the prospect of life. Imagine for a moment the sheer diversity of worlds out there. Thousands upon thousands of exoplanets discovered orbiting distant stars, each a unique laboratory of cosmic physics. And among them, a significant proportion are likely locked in a gravitational embrace with their parent stars, far more intense than anything we see in our backyard. Let's start with the most common stars in our galaxy, the M-dwarfs. These are smaller, cooler, and dimmer than our Sun, but they make up about 70% of all stars. Because they're so dim, their habitable zones, the region where liquid water could exist on a planet's surface, are incredibly close to the star. And when planets orbit that close, guess what does? Guess what happens? Tidal locking becomes almost inevitable. This leads us to a fascinating, genuinely strange class of worlds often dubbed eyeball planets, or Terminator worlds. Picture this, a planet where one side is perpetually bathed in the relentless scorching light of its star, locked in an eternal day. The other side, plunged into an unending, frigid night. And between these two extremes lies a narrow, tantalizing strip of perpetual twilight, the Terminator zone. Think about that for a moment. No sunrises, no sunsets, just an endless, unwavering cosmic spotlight on one hemisphere. The implications for these worlds are profound. On the day side, temperatures could soar, evaporating any surface water and baking the landscape dry, perhaps even creating oceans of molten rock if the star is hot enough. Clouds of rock vapor might even form and rain down silicate droplets. On the night side, temperatures would plummet to extreme lows, freezing any atmosphere solid or creating vast glaciers of exotic ices. But what about that Terminator zone? This narrow band, perpetually in twilight, could be the sweet spot. Here, the temperatures might be just right for liquid water to exist, either in lakes, rivers, or even a global ocean that wraps around the planet. Imagine a world where life, if it exists, has adapted to live in a strip of eternal dawn or dusk with a sky that never truly brightens or darkens, only shifts subtly in hue. The winds on such a planet would be ferocious, constantly trying to equalize the extreme temperature differences between the day and night sides, creating global atmospheric currents unlike anything we experience on Earth. These winds could carry moisture from the night side, where it sublimates, to the Terminator zone, where it condenses as rain, potentially sustaining life. Tidal locking in this scenario doesn't just shape the planet's rotation, it dictates its entire climate, its geology, and potentially its biology. But M-dwarf planets are just one facet of this cosmic tapestry. Let's talk about the true titans of tidally locked extremes, the hot Jupiter. These are gas giants, comparable in size to Jupiter, but orbiting incredibly close to their stars, sometimes closer than Mercury is to our Sun. Their orbital periods can be measured in mere days or even hours. And at such proximity, the tidal forces are absolutely immense, virtually guaranteeing that these behemoths are tidally locked. What does tidal locking mean for a hot Jupiter? It means one side is permanently seared by its star, reaching temperatures that can vaporize rock and metal. We're talking thousands of degrees Celsius. The other side, while still incredibly hot due to atmospheric circulation, is comparatively cooler. This extreme temperature differential drives supersonic winds, churning atmospheres at speeds of thousands of miles per hour. Imagine a constant planet-wide hurricane that never dissipates. Some hot Jupiters even have atmospheres so hot they glow, or exhibit strange phenomena like iron rain, where vaporized metals condense and fall as liquid droplets on the cooler night side. Tidally locked hot Jupiters are truly alien worlds, testaments to the raw power of gravity and stellar radiation. Then there are the super-Earths and mini-Neptunes, planets larger than Earth but smaller than Neptune, a class of exoplanets we don't even have in our own solar system. Many of these, especially those found close to their stars, are also likely tidally locked. What impact does this have on a solid, rocky world, perhaps with a thick atmosphere or even a global ocean? The tidal stresses on their interiors could be immense, leading to more frequent and powerful volcanic activity, shaping their crusts in entirely unique ways. The constant tug and pull, the flexing of the planetary body could generate significant internal heat, potentially driving plate tectonics or sustaining subsurface oceans even without a strong radioactive decay heat source. And speaking of internal heat, let's revisit the concept of tidal heating on a much grander scale. We saw it with Io, Jupiter's volcanic moon, where the constant stretching and squeezing from Jupiter's gravity generates enough friction to keep its interior molten. Now imagine an exoplanet, perhaps a super-Earth in an elliptical orbit around its star, and also tidally locked. This combination is a recipe for extreme internal heating. As the planet swings closer to its star, the tidal forces increase, stretching it more. As it moves further away, the forces decrease and it relaxes. This continuous flexing, this cosmic kneading, can generate incredible amounts of heat within the planet's interior. The result? Worlds that could be entirely molten, with surfaces of glowing lava, crisscrossed by the colossal volcanoes constantly erupting. Or perhaps worlds with such intense geological activity that their entire crust is constantly being recycled, dramatically influencing their atmospheric composition and potential for life. Tidal heating, when amplified on exoplanet scales, isn't just a curiosity. It's a fundamental geological engine, shaping the very crust and atmosphere of these distant worlds. The existence of tidally locked exoplanets forces us to rethink our assumptions about habitability. For a long time, the prevailing wisdom was that tidal locking to an M-dwarf star would be detrimental to life, creating too extreme a climate. But as we explore the nuances, we realize it's far more complex. The strong winds could distribute heat, preventing runaway freezing or boiling. The constant twilight of the terminator zone could offer a stable, moderate environment. And the persistent tidal flexing could even provide a deep-sea energy source for chemosynthetic life, much like on Earth's ocean floors, independent of sunlight. The more we learn about these distant, tidally locked worlds, the more we appreciate the elegant, brutal mechanics of gravity. Tidal locking isn't some rare cosmic quirk. It's a widespread, powerful force that sculpts planets, dictates climates, and fundamentally influences the very architecture of planetary systems across the galaxy. From the subtle slowing of Earth's rotation to the infernal glow of a hot Jupiter's dayside, the principle remains the same. The differential gravitational pull of a massive body on its orbiting companion. It's a testament to the fact that the universe is far more imaginative than we are. The simple observation of our moon always showing us the same face has led us down a rabbit hole of scientific discovery, revealing a cosmic ballet of forces that shapes everything from the length of our day to the potential for life on worlds light years away. So the next time you look up at our familiar moon, remember its profound secret. Remember that its steady gaze is a whisper from the cosmos, hinting at the truly astonishing and diverse worlds shaped by the very same forces far beyond our wildest dreams. It's a reminder that the universe is a place of constant motion, constant change, and endless wonder. What are your thoughts on these extreme tidally locked worlds? Do you think life could thrive in a terminator zone or on a supervolcanic exoplanet? Drop a comment below and let's explore these cosmic possibilities together. We've journeyed through the intricate dance of gravity, from our familiar moon's unchanging face to the exotic superheated world orbiting distant stars. We've unravelled the elegant, brutal mechanics of tidal locking, recognizing it not as a mere astronomical curiosity, but as a profound force shaping the very destiny of planets. In Chapter 4, we touched upon how this cosmic embrace forces us to reevaluate our understanding of habitability, especially around the most common stars in our galaxy. Of galaxies, the M dwarfs. Now let's truly dive into the heart of that re-evaluation. What does life look like, or rather, where could it exist on a world forever caught in its star's gravitational gaze? Imagine yourself standing on a planet tidally locked to its star. This isn't just a thought experiment, it's the reality for potentially billions of worlds out there. On one side, the day side, your star hangs perpetually in the sky, an unmoving, searing beacon. Here, temperatures can climb to unimaginable highs, boiling away any surface water and creating a desolate, parched landscape. On the opposite side, the night side, eternal twilight gives way to an unending, frigid night. The star is never seen and temperatures plummet, freezing gases out of the atmosphere and creating a desolate, icy wasteland. Sounds pretty bleak for life, right? But wait, remember those eyeball planets and Terminator worlds we mentioned? The truth, as always in the cosmos, is far more nuanced and astonishing. The key to potential habitability on these worlds lies in their atmosphere and, if present, their oceans. These aren't just passive blankets, they are dynamic planet-spanning systems of heat distribution, working tirelessly to try and equalize the extreme temperature differences. Let's start with the atmosphere. On a tidally locked planet, the intense, unceasing heat from the dayside substellar point, the spot directly facing the star, creates a massive permanent updraft. Air heats up, becomes less dense, and rises high into the atmosphere, much like a giant, continuous thermal column. This rising air then flows outward, both towards the perpetually dark night side and along the Terminator zone. As it reaches the night side, it cools, becomes denser, and sinks back down, completing a colossal planet-wide circulation cell. Think of it like a giant, slow-motion convection oven on a planetary scale. This constant atmospheric flow means that the night side isn't necessarily a completely frozen, airless void. The dayside air, superheated and carrying vast amounts of energy, is constantly being ferried across the planet. This creates incredibly strong, persistent winds, especially along the Terminator zone, that narrow band of perpetual twilight separating the endless day from the endless night. These winds could be supersonic, howling across the landscape with relentless force, shaping geology and presenting a formidable challenge to any aspiring life forms. However, these winds are also the planet's salvation. They act as a cosmic conveyor belt, transporting heat from the scorching day side to the freezing night side, preventing the complete atmospheric collapse that might otherwise occur on the night side as gases freeze out. The effectiveness of this heat transfer is crucial. If the atmosphere is thick enough and the winds are strong enough, they can moderate temperatures sufficiently to create a band of temperate conditions. And this, dear explorers, brings us back to the Terminator zone. This isn't just a line on a map, it's a dynamic, potentially life-sustaining region. Here, the star would always be low on the horizon, bathing the landscape in an eternal orange-red twilight. The constant winds would still be a factor, but the temperatures might just be perfect for liquid water to exist on the surface. Imagine a world where the sun never rises nor sets, where the sky is a permanent gradient of dawn and dusk, and where life might thrive in this unending twilight. But it's not just about temperature. The atmospheric circulation also has profound implications for water. On the day side, the intense heat would cause massive evaporation. This water vapour would then be carried by these powerful winds towards the cooler night side. As it travels, it would eventually cool enough to condense, forming clouds and potentially precipitating as rain or snow on the night side. This could lead to a scenario where the day side is a vast desert, while the night side is covered in glaciers and ice sheets, with a band of liquid water, rivers and lakes nestled in the Terminator. Now let's consider the profound influence of oceans. If a tidally locked planet possesses substantial liquid water oceans, the game changes dramatically. Water has an incredibly high heat capacity, meaning it can absorb and store vast amounts of thermal energy. Oceans on these worlds would act as colossal heat reservoirs and distributors, far more efficient than the atmosphere alone. Imagine a global ocean on a tidally locked world. The dayside ocean would absorb immense, heat from the star. But powerful planet-spanning ocean currents would then carry this warmth towards the night side. These currents, driven by temperature differences and the planet's rotation, however slow, could effectively moderate global temperatures, preventing the extreme hot and cold zones from being quite so extreme. The entire planet might maintain a more uniform, temperate climate, perhaps even supporting life across a wider swath of its surface, not just the Terminator. We could be looking at superocean planets where life, if it arose, might be predominantly aquatic, adapting to continuous twilight or even deep-sea environments. This interplay of atmosphere and ocean fundamentally reshapes our understanding of habitability. What was once considered a death sentence for life, being tidally locked, now presents a fascinating array of new possibilities. We are forced to broaden our search parameters beyond Earth 2.0 and consider Terminator 1.0 or Aquatic 3.0 as equally viable candidates for hosting extraterrestrial organism. But what kind of life could exist in such an environment? Think about the challenges: constant strong winds, perpetually dim red-shifted light if orbiting an M-dwarf, and a stable, unchanging climate gradient. Photosynthesis, the basis of most life on Earth, would need to adapt to low light levels and potentially different light spectra. Perhaps photosynthetic organisms would be dark pigmented to absorb every available photon, or they might form vast wind-resistant mat or burrow underground. Animals would need adaptations for powerful winds, perhaps streamlined bodies, strong anchors, or even subterranean lifestyles. The Terminator Zone could harbour unique ecosystems, with flora and fauna specially adapted to the eternal twilight, perhaps with bioluminescent features to communicate in the dim light. The search for biosignatures on these tidally locked worlds becomes even more intriguing. If life thrives in the Terminator Zone, what atmospheric gases might it produce? High levels of oxygen, methane, or ozone in non-equilibrium with the planet's geology could still be telltale signs. But we might also look for more exotic biosignatures, or even patterns in surface reflectivity that suggest vast adapted biomes. Our telescopes and future missions are designed to peer into these alien atmospheres, seeking these subtle clues. Beyond the atmosphere and oceans, the internal dynamics of these planets also play a role. Remember how tidal forces can generate internal heat, especially for the planets in elliptical orbits. This tidal heating could be crucial for maintaining geological activity, such as volcanism and plate tectonics. On Earth, these processes are vital for recycling carbon dioxide, regulating our climate and providing essential nutrients. For a tidally locked world, internal heating could sustain a geologically active core, ensuring a long-term carbon cycle and potentially releasing gases that help form a protective atmosphere. It's a delicate balance, an elegant, brutal cosmic engine that could foster life in ways we are only just beginning to comprehend. So, as we gaze at the vast tapestry of the cosmos, the phenomenon of tidal locking, initially perceived as a barrier to life, transforms into a sculptor of unique biological niches. It expands our cosmic imagination, pushing us to consider a universe teeming with far more diverse forms of life and habitable environments than previously thought. The next time you look at our moon, always presenting the same face, remember it's a silent testament to a universal force, one that might just be creating countless worlds where life has found a way to flourish, even in the most extreme mind-bending conditions imaginable. The universe, you see, is far stranger and more wonderful than we can ever fully grasp. And the journey to understand its secrets, like the strange truth about the moon's motion, is one we are only just beginning. What other cosmic wonders await our discovery? What further re-evaluations will we have to make as we continue to explore? We can't wait to find out with you. Until then, keep looking up, keep asking questions, and keep dreaming science. Welcome back, cosmic explorers, to Dreamy Science. We've journeyed through the subtle dance of our moon, witnessed the widespread phenomenon of tidal locking across our own solar system, and even ventured to the extreme fascinating worlds beyond, exploring how tidal forces sculpt exoplanetary landscapes and potentially foster life. We've seen gravity act as a gentle sculptor, slowing rotations, maintaining oceans, and creating habitable zones in the most unexpected places. But what happens when this elegant, powerful force of gravity pushes beyond mere shaping? What happens when the tidal stresses become so immense that they don't just lock a world, but threaten to tear it apart? Today we delve into the truly extreme, the moments when gravity's embrace becomes a crushing grip, when worlds are ripped asunder, and the very fabric of celestial bodies is redefined by the relentless power of tidal forces. This is where the universe reveals its brutal beauty, its capacity for creation and destruction, all orchestrated by the same fundamental laws we've been exploring. Imagine, if you will, a moon orbiting its giant planet or a planet circling its star. We've talked about the differential gravitational pull, how the side of the moon closer to the planet feels a stronger tug than the far side. This difference creates the tidal bulges, the very mechanism behind tidal locking and heating. But as an object gets closer and closer to a massive body, this differential force doesn't just create bulges, it stretches and distorts the object more and more violently. There comes a point, a critical distance, where the host body's tidal forces become stronger than the orbiting object's own self-gravity, the force holding it together. This isn't just a gentle tug-of-war anymore. It's a cosmic arm-wrestling match where one side is destined to lose. We call this critical boundary the Roche limit. Beyond this point, an object held together only by gravity, like a moon or a planet, cannot survive. It will be ripped apart, pulled into a stream of debris that often forms spectacular rings around the more massive body. Think about that for a moment. The same force that so elegantly locks our moon into its synchronous orbit can, under different circumstances, utterly dismantle another world. It's a profound and a mind-bending truth, right? Our own solar system offers stunning examples of this destructive power. Saturn's magnificent rings, for instance, are widely believed to be the remnants of a moon, or perhaps several moons that ventured too close to the gas giant and crossed its Roche limit. The immense tidal forces of Saturn shredded these icy bodies, scattering their fragments into the dazzling, intricate system we marvel at today. The shattered pieces, unable to recoalesce due to Saturn's continued tidal pull, spread out into the flat pancake-like rings, each particle still orbiting in a complex dance dictated by gravity. And it's not just moons. Imagine a comet, a dirty snowball from the outer reaches of the solar system, making a daring dive towards the sun. As it gets closer, the sun's tidal forces begin to act upon it. We've seen comets literally break apart into multiple pieces as they approach the sun, their icy nuclei unable to withstand the intense gravitational stretching. Each fragment then continues its journey, a testament to the sun's overwhelming power. But the Roche limit is just the beginning of understanding ultimate tidal extremes. What about hypertidal heat? Heating. We discussed Io, Jupiter's innermost Galilean moon, as the most volcanically active body in our solar system, its interior constantly kneaded and heated by Jupiter's powerful tides and orbital resonances with its sister moons. But imagine that effect magnified 1,000-fold. On some exoplanets, particularly those known as hot Jupiters or super-Earths orbiting incredibly close to their parent stars, the tidal forces are so colossal that the internal heating is beyond anything we witness in our own solar system. These planets are not just tidally locked, they are tidally stressed to an unimaginable degree. Their interiors are a maelstrom of molten rock constantly churning, perhaps even glowing from the sheer frictional heat. We could be talking about worlds where the entire mantle is in a state of perpetual violent convection, driving volcanism on a scale that beggars belief, or creating vast, deep, subsurface magma oceans. Some theoretical models suggest that such extreme tidal heating could even strip away a planet's atmosphere or significantly contribute to its geological evolution, creating an environment unlike anything we can easily picture. And what about the most extreme tidal disruptions? When a star or even a black hole encounters a passing planet or star, the consequences are truly cataclysmic. Picture a star wandering too close to a supermassive black hole at the center of a galaxy. As it crosses the black hole's event horizon, or even just approaches its Roche limit, the differential gravity is so immense that the star is not just torn apart but literally spaghettified. Its material is stretched into a long, thin stream, like toothpaste being squeezed from a tube, glowing fiercely as it's consumed by the black hole. This isn't just theoretical. Astronomers have observed these tidal disruption events in distant galaxies, providing direct evidence of gravity's ultimate destructive power. Now let's broaden our scope even further. We've primarily talked about one planet orbiting one star or one moon orbiting one planet, but the universe is full of binary star systems, where two stars orbit each other, and even worse, multi-star systems. How do tidal forces play out in these intricate cosmic ballets? Imagine a planet orbiting one star in a close binary system. The gravitational pull of the companion star introduces a whole new layer of complexity. It can perturb the planet's orbit, making it more elliptical, which in turn can lead to intense tidal heating within the planet itself, even if it's not particularly close to its primary star. These constantly changing gravitational vectors can create a dynamic, unpredictable tidal environment, potentially leading to bursts of geological activity, or even destabilizing the planet's orbit over cosmic timescales. Some planets might even orbit both stars in a wider binary system, experiencing a constantly shifting tidal landscape as the two suns move around each other. The potential for extreme tidal forces and exotic orbital resonances in these multi-body systems is truly mind-boggling, painting a picture of cosmic mechanics far more intricate than we often consider. And let's not forget the grander scales, galactic tidal forces. Our own Milky Way galaxy, a massive spiral, is constantly interacting gravitationally with its smaller satellite galaxies like the Magellanic Clouds or the Sagittarius dwarf spheroidal galaxy. The Milky Way's immense gravitational pull exerts tidal forces on these smaller galaxies, stretching them, pulling away stars and gas, and eventually tearing them apart, absorbing their material into our own galaxy. These galactic tidal streams are like cosmic rivers of stars, evidence of the universe's ongoing evolution and the pervasive reach of gravity, even across unfathomable distances. It's the same fundamental principle we see in our moon and Earth, just scaled up to cosmic proportions. Isn't that incredible? So we've explored tidal forces as creators of stability, as sculptors of worlds, and now as agents of destruction. But what about the ultimate cosmic destinies of these tidally locked systems? We touched on Earth's future, how it might one day become tidally locked to the moon, and how both will eventually face the fate of our evolving sun. As our sun ages, it will swell into a red giant, expanding to perhaps engulf Mercury, Venus, and possibly even Earth. What happens to the tidally locked planets and moons that survive this stellar transformation? Some might be vaporized, others might be flung into interstellar space. But some, particularly those orbiting more distant stars that become white dwarfs, the dense, hot remnants of stars like our Sun, could experience a strange new existence. Imagine a tidally locked exoplanet, perhaps a stripped-down rocky core, orbiting a white dwarf. The gravitational field of a white dwarf is incredibly intense due to its immense density. Such a planet would be subject to powerful tidal forces, potentially leading to further geological activity, or even a second phase of tidal heating. These Chthonian planets, as they are sometimes called, represent a kind of planetary afterlife tidally bound to a stellar corpse, forever locked in a dim, silent dance. The conditions for life would be vastly different, perhaps even impossible, but the sheer persistence of these tidally locked remnants speaks to the enduring power of gravity. Ultimately, the story of tidal forces is a story of our cosmic equilibrium and relentless change. From the subtle slowing of Earth's rotation to the violent spaghettification of stars, gravity's differential pull is a universal architect. It shapes the rotation of moons, maintains the internal heat of icy worlds, creates unique habitats on distant exoplanets, and, when pushed to its extreme, tears celestial bodies apart, recycling their mere material into new cosmic structures. The universe, in its elegant, brutal mechanics, is always in motion, always evolving. Tidal locking isn't a static state, but a dynamic balance, a temporary truce in the ongoing gravitational tug-of-war. And knowing this, understanding the profound and far-reaching effects of these forces, allows us to look up at our moon, or gaze at the distant stars with a renewed sense of wonder and a deeper appreciation for the intricate cosmic ballet unfolding all around us. What are your thoughts on these ultimate tidal extremes? Does the idea of a planet being torn apart by gravity fill you with awe or a touch of cosmic dread? Drop a comment below and let us know. And if you're enjoying this journey through the strange truth of cosmic motion, don't forget to like this video and subscribe to Dreamy Science for more explorations into the wonders of our universe. We're just scratching the surface of the universe's secrets, and there's so much more to uncover together. In our last cosmic journey, we peered into the abyss, witnessing the raw, destructive power of tidal forces, the rush limit tearing worlds asunder, stars being spaghettified by black holes, and galaxies locked in a slow gravitational death embrace. It was a brutal ballet, an elegant, brutal mechanics of cosmic dissolution. But here's the profound truth, dear cosmic explorers. Tidal forces aren't just agents of destruction. Oh no, far away we go, more far from. They're also the universe's most patient, persistent and powerful sculptors, constantly reshaping, refining and even creating the celestial tapestry around us. Think about that for a moment. The very same forces that can rip a moon apart can also shepherd planets into new orbits, ignite stellar explosions, and even forge the majestic spiral arms of galaxies. Today we're diving into the long game, exploring how these pervasive gravitational whispers evolve entire systems, guiding their destinies across billions of years. We're talking about the cosmic evolution, driven by the relentless, ubiquitous dance of tides. Let's begin with the intimate embrace of here binary star systems, a topic we touched upon in our last chapter. You know, systems where two stars orbit a common centre of mass. These aren't anomalies, they're incredibly common, comprising perhaps half of all stars in the galaxy. And in these close-knit relationships, tidal forces are the ultimate matchmakers and long-term planners. Imagine two stars born from the same swirling cloud of gas, gradually drawing closer. Their mutual gravitational pull, especially the differential force across their vast stellar bodies, starts to exert a powerful torque. Just like the Earth's gravity slowed our moon's spin, these stellar tides act as cosmic brakes, gradually forcing the stars into a state of mutual tidal locking. Eventually each star presents the same face to its companion, their rotations synchronized with their orbital period. This isn't just a theoretical concept. We observe many such tidally locked binary systems, their silent, eternal gazes fixed upon each other. But the story doesn't end with a gentle lock. In even closer binary systems, especially when one star begins to evolve off the main sequence, perhaps swelling into a red giant, the tidal forces become truly transformative. As the outer layers of the evolving star expand, they can cross a critical boundary called the Roche lobe, the gravitational domain of that star. When this happens, its material spills over, like water overflowing a cup, and begins to flow onto its companion. This is mass transfer, a spectacular phenomenon where tidal forces literally facilitate the cannibalization of one star by another. This isn't just a stellar drama, it's a cosmic engine. This transferred material, often forming an incredibly hot, swirling accretion disk around the companion star, can ignite spectacular events. Think about novae, where a white dwarf siphons hydrogen from its companion until enough accumulates on its surface to trigger a runaway thermonuclear fusion reaction, briefly flaring into incredible brightness. Or even more dramatically, Type Ia supernovae. the standard candles of the universe, which occur when a white dwarf accumulates so much mass from its companion that it exceeds the Chandrasekhar limit, leading to a catastrophic explosion that obliterates the star entirely. Tidal forces in this context are not merely destructive. They are the catalysts for some of the most powerful and illuminating events in the cosmos, reshaping stellar remnants and enriching the interstellar medium with heavy elements essential for future generations of stars and planets. And what about the ultimate fate of the closest, most massive binary systems? As these stellar pairs orbit ever closer, their intense gravitational interactions generate ripples in the fabric of space-time itself, gravitational waves. These waves carry away energy, causing the stars to spiral inwards, accelerating their descent into a final cataclysmic merger. Imagine two neutron stars, or even two black holes, locked in a death spiral, their tidal forces becoming so immense that they distort space-time, culminating in a violent collision that shakes the very foundations of the universe, sending out gravitational waves that we can now detect here on Earth. This isn't just science fiction. It's the elegant, brutal truth of cosmic evolution, driven by the relentless power of tides. Now let's zoom out a bit and consider how tidal forces sculpt entire planetary systems. We've seen how our moon's tides have shaped Earth's rotation and its own orbit, but this principle scales up dramatically. Think about the early, chaotic days of a young planetary system, still forming within a swirling protoplanetary disk of gas and dust. Tidal interactions between the nascent planets and this massive disk are thought to be a primary driver of orbital migration. Planets aren't born in their final orbits, they move. Giant planets like Jupiter may have migrated inwards then outwards, pushing and pulling smaller inner planets with them. This grand gravitational dance, largely orchestrated by tidal forces, can dramatically reshape the architecture of a planetary system, determining where planets ultimately settle, or even if they get ejected entirely. Without tidal forces, the planetary systems we observe might look entirely different, perhaps even preventing the conditions necessary for life as we know it. And once planets are established, tidal forces continue their relentless work, often maintaining delicate orbital resonances. Remember Jupiter's Galilean moons locked in their precise rhythmic dance. That's tidal forces at work maintaining those relationships, preventing collisions, and in Eo's case generating immense internal heat. These resonances aren't just neat coincidences, they are the stable, long-term outcomes of billions of years of tidal interactions, a testament to the universe's elegant self-organizing principles. Tidal forces are also fundamental in the formation and evolution of moons and ring systems. Saturn's magnificent rings, for example, are widely believed to be the remnants of a moon, or moons, that ventured too close to the giant planet, crossing its Roche limit and being torn apart by its immense tidal gravity. The fragments then spread out, forming the breathtaking icy spectacle we see today. Even our own moon's gradual recession from Earth, driven by tidal friction, is a testament to this ongoing evolution, slowly but surely altering the dynamics of our home system. But the cosmic sculptor doesn't stop at stars and planets. Its influence extends to the grandest scales, reshaping entire galaxies. We touched on galactic tidal forces in Chapter 6, how they can strip away stars from dwarf galaxies or distort the edges of larger ones. But let's delve deeper into their creative role. Consider the majestic spiral arms of galaxies like our own Milky Way. While their precise formation mechanism is still an active area of research, tidal forces are thought to play a significant role. Interactions with nearby satellite galaxies or even internal tidal stresses from the distribution of dark matter can create density waves that sweep through the galactic disk, compressing gas and dust and triggering bursts of star formation. The very structures that make galaxies so beautiful and vibrant might be, in part, a manifestation of these colossal tidal whispers. And then there are galaxy mergers, the ultimate tidal dance on a cosmic scale. When two galaxies collide, it's not like two billiard balls smashing together. Individual stars rarely hit each other. Instead, the immense gravitational fields of both galaxies exert powerful tidal forces on each other, stretching, pulling, and distorting their shapes. Spiral arms unravel, gas clouds collide and compress, triggering furious bursts of star formation, and the galaxies gradually merge into one, often more massive, elliptical galaxy. This isn't just a destructive process. It's a transformative one, creating new galactic structures and driving cosmic evolution on the grandest stage. Our own Milky Way is on a collision course with the Andromeda Galaxy in about 4.5 billion years, destined for just such a tidal merger, a future giant elliptical we call Milkomeda. So we see that tidal forces are the silent, ubiquitous architects of the cosmos, shaping everything from the spin of a tiny moon to the majestic collision of galaxies. They are the reason for the moon's unchanging face, the searing volcanism of Io, the potential habitability of exoplanets, the violent birth of supernovae, and the grand swirling dance of galactic evolution. And what about the ultimate destinies of the tidally locked systems we've explored? In the far, far future, long after their stars have died, some of these worlds might still exist, orbiting the cold, dense remnants of their stellar parents. White dwarfs, neutron stars, or even black holes. We touched on lunar planets in the last chapter, the rocky cores of gas giants that have been stripped bare by their stars' intense radiational proximity. Tidal forces will continue their relentless work on these ultimate survivors, perhaps even driving geological activity on these seemingly dead worlds, or slowly drawing them into their host's gravitational maw. The universe, in its elegant brutality, never truly rests. Its components are always in motion, always interacting, always evolving under the omnipresent influence of gravity and its differential manifestation, the tides. From the gentle slowing of a moon's rotation to the colossal reshaping of galactic empires, tidal forces are a fundamental thread woven into the fabric of reality. They are not merely an interesting footnote in astrophysics. They are the very engines of cosmic change, both destructive and profoundly creative. They remind us that the universe is a dynamic, ever-evolving entity, constantly being sculpted by forces that are as invisible as they are powerful. As we conclude this exploration of the strange truth about cosmic motion, we're left with a deeper appreciation for the intricate mechanics of the universe. Tidal forces, in all their manifestations, are a testament to the elegant, brutal, and utterly fascinating principles that govern our cosmos. They show us that even the most subtle tug can, over astronomical timescales, lead to the most profound transformations. Join us next time as we wrap up our journey, perhaps pondering the secrets yet to uncover, and how our understanding of these cosmic sculptors continues to evolve. Until then, keep looking up, and keep wondering about the incredible universe we call home. The universe we've discovered is not a static tableau, but a grand ongoing performance, a relentless cosmic ballet where every player, from the smallest moon to the grandest galaxy, is in constant motion, ever-changing. And at the heart of so much of this ceaseless transformation are those elegant, brutal mechanics we've been exploring, tidal forces. We've seen them sculpt moons, ignite volcanoes, create habitable zones, and even rip apart worlds. But what does this relentless process of creation and transformation truly mean for the future? How do these forces continue their work over the truly astronomical timescales, shaping not just moments, but entire epochs of cosmic destiny? Let's cast our gaze far, far into the future, beyond the mere billions of years we typically contemplate, and consider the ultimate fate of systems shaped by tides. We spoke of Earth eventually becoming tidally locked to our moon, a distant future where both celestial bodies would forever show each other the same face. Imagine that, a silent, eternal embrace, the cosmic dance finally synchronized. But even that state of perfect harmony isn't truly eternal, is it? Because the universe has even grander architects at play, and even more profound forces waiting in the wings. Our sun, that benevolent star that warms our planet and fuels all life, is itself on an evolutionary journey. In roughly 5 billion years, it will exhaust the hydrogen fuel in its core and begin its transformation into a red giant. As it swells, its outer layers will expand dramatically, potentially engulfing Mercury, Venus, and possibly even Earth. What happens to the delicate tidal balance we've so painstakingly unravelled then? The increased gravitational pull from the vastly expanded Sun would overwhelm the Earth-Moon system, drawing our planet and its companion closer, or perhaps even stripping the Moon away entirely. The very forces that brought them into their intricate dance would, in this final act, orchestrate their dissolution. Think about the irony. The same gravitational forces that birthed our Moon, locked its rotation, and drove its slow recession would eventually be subsumed by the Sun's final fiery embrace. It's a powerful reminder that cosmic processes are nested within each other, a hierarchy of influence playing out across unfathomable durations. The Earth-Moon tidal lock, a profound achievement of cosmic mechanics, is but a fleeting moment in the vast timeline of stellar evolution. And this isn't just a local phenomenon, it's a universal truth. Every tidally locked exoplanet, every mutually locked binary star system, every moon warmed by tidal heating, they all exist within the larger, evolving context of their host stars and galaxies. As stars age, expand or die, they fundamentally alter the tidal landscapes around them. A white dwarf, the dense remnant of a star like our Sun, can exert immense tidal forces on any surviving planets, potentially ripping them apart or causing them to spiral inward. Neutron stars and black holes, with their incredibly intense gravity, are the ultimate tidal destroyers, capable of spaghettifying entire stars, as we briefly touched upon. The universe in its grand design is constantly resetting, reshaping and reimagining itself through these interactions. But how do we, as curious observers, even begin to detect it? These grand cosmic ballets playing out across light years and billions of years. This brings us to another fascinating aspect of tidal forces, their role as cosmic messengers and detectives. We don't just observe the effects of tides, sometimes we can detect the very waves they generate. Remember when we discussed the inspiral and merger of massive objects like neutron stars or black holes? These cataclysmic events are driven by extreme tidal forces. As two such behemoths draw closer, their mutual gravitational tugs become so immense that they distort space-time itself, sending ripples or gravitational waves outward but at the speed of light. Imagine two cosmic dancers spinning ever faster, their embrace tightening until they finally merge in a spectacular cosmic collision. That final violent pirouette generates a burst of gravitational waves that travels across the universe. And we can hear them. Well, not with our ears, but with incredibly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO. These observatories are designed to detect the minuscule stretching and squeezing of space-time caused by passing gravitational waves. When LIGO first detected these waves in 2015, originating from the merger of two black holes, it was a profound confirmation of Einstein's theory of general relativity and a direct observation of the universe's most extreme tidal events. It was like suddenly being able to hear a symphony that had been playing silently for billions of years, a profound and mind-bending truth. Think about that for a moment. We are not just inferring tidal forces from their visible consequences, like a planet's rotation or a moon's volcanism. We are directly detecting the very fabric of space-time being warped and rippled by these forces. It's a testament to the power of scientific inquiry and technological ingenuity, allowing us to peek behind the curtain of the most violent cosmic events. Beyond these cataclysmic events, tidal forces also leave more subtle signatures that help us understand distant worlds. When we observe exoplanets, especially those orbiting very close to their stars, the effects of tidal locking are often assumed. But we can also look for evidence of tidal heating. If an exoplanet or exomoon shows unexpected thermal emissions, or if its atmosphere reveals signs of intense geological activity, it could be a telltale sign of powerful tidal forces at work within its interior. These tidal fingerprints allow us to infer the internal structure, composition, and even the potential habitability of worlds light years away. For instance, detecting a thick, water-rich atmosphere around a super-Earth that's tidally locked to an M-dwarf star might suggest a tidally heated interior maintaining a liquid ocean beneath the surface, much like Europa or Enceladus. So tidal forces aren't just architects, they're also profound communicators, sending signals across the vastness of space and time. They are the silent symphony playing out across the cosmos, orchestrating change, driving evolution, and leaving behind clues for us to decipher. This brings us to a deeper appreciation for the universality of these forces. We began our journey with our familiar moon, but we quickly ventured to Mercury, Jupiter's moons, Pluto Charon, and then to exoplanets and galaxies. The principles remain the same: differential gravity creating bulges, generating torque, transferring angular momentum, and manifesting as either creative or destructive power. This universality is one of the most beautiful aspects of physics. The same laws that govern the tides in your local ocean are at play in the formation of Saturn's rings and the merger of supermassive black holes. It's an elegant, brutal consistency that underpins the entire cosmos. And yet, our understanding is far from complete. The universe is an endlessly complex tapestry, and while we have unravelled many threads, countless others remain a mystery. We are still refining our models of how tidal forces interact with planetary interiors, how they influence atmospheric escape on exoplanets, or how they precisely contribute to the formation of specific orbital resonances in multi-planet systems. Every new observation, every new gravitational wave detection, every new exoplanet discovery adds another layer to our understanding, sometimes confirming our theories, sometimes challenging them, and always pushing the boundaries of our knowledge. The journey of scientific discovery is itself a relentless process. Much like the tidal forces we've been exploring, it's an ongoing quest driven by curiosity and a desire to understand the fundamental mechanics of existence. We as humans stand on a small planet gazing out at an immense and wondrous cosmos, trying to make sense of its intricate workings. And in tidal forces, we find one of the most powerful, pervasive and profound architects of that cosmos. From the gentle ebb and flow of our oceans to the violent destruction of stars, from the synchronization of a moon's spin to the grand ballet of galactic mergers, tidal forces are everywhere, shaping everything. They are a constant reminder that the universe is dynamic, alive and forever in motion. They show us that apparent stillness, like our moon always showing the same face, is often just a manifestation of a deeper, more profound motion, a perfect synchronization born from eons of gravitational interaction. So, the next time you look up at our moon, or ponder the distant twinkle of a star, remember the elegant, brutal mechanics at play. Remember the constant push and pull, the give and take of angular momentum, the ceaseless dance of gravity. It's a story written in the very fabric of space-time, a cosmic secret whispered across billions of years, and one that we, as curious inhabitants of this universe, are only just beginning to truly appreciate. The wonder, you see, never truly ends. We've journeyed through the cosmos, exploring the incredible reach of tidal forces, from our moon's silent spin to the fiery heart of Io, from the icy geysers of Enceladus to the scorching winds of hot Jupiters, and even to the grand spiraling embrace of merging galaxies. We've seen how these elegant, brutal mechanics shape worlds, tear stars apart, and orchestrate a vast, intricate cosmic ballet. But how do we, down here on Earth, know all this? How do we detect these invisible hands at work across unimaginable distances, deciphering the profound truths they whisper about the universe's internal structure and even the potential for life? This, dear cosmic adventurers, is where the story of tidal forces truly becomes one of cosmic detective work. The universe is constantly leaving tidal fingerprints, subtle clues that, with the right instruments and a keen scientific eye, we can piece together to reveal its deeper secrets. It's a thrilling frontier of discovery, where we're not just observing the aftermath of tidal interactions, but actively listening to the universe's rumbles and seeing the telltale signs of its most fundamental forces. Let's dive into the fascinating ways we're becoming increasingly adept at this cosmic sleuthing, pushing the boundaries of what we can perceive and understand. First, imagine a universe not just filled with light, but also with ripples. Ripples just in the very fabric of space-time itself. These are gravitational waves, and they're perhaps the most direct way we can hear the universe's most violent tidal interactions. Think about that for a moment. Space-time isn't a static stage, but a dynamic, flexible canvas. When massive objects accelerate, especially in extreme energetic events like the collision of black holes or neutron stars, they create disturbances that propagate outwards at the speed of light. For decades, these gravitational waves were a prediction of Einstein's theory of general relativity, but an elusive one. Then, in 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, experiment made history by directly detecting them. What did they hear? The final cataclysmic merger of two black holes, a tidal interaction so extreme it shook the very foundations of reality. Since then, LIGO and its partners Virgo and Cagra have detected dozens of these events, primarily black hole mergers, but also the incredible collision of two neutron stars. And it's these neutron star mergers that are particularly fascinating for our discussion of tidal forces. Neutron stars are the super-dense remnants of collapsed massive stars, packing more mass than our Sun into a sphere the size of a city. When two of these incredibly dense objects spiral inward towards each other, locked in a death dance, their mutual gravitational pull becomes immense. Tidal forces stretch into form each neutron star, pulling them into elongated shapes just before they finally merge. This tidal deformation isn't just a side effect, it's imprinted directly onto the gravitational wave signal. By meticulously analysing the precise waveform of these gravitational waves, we can extract crucial information. The masses of the neutron stars, their spins, their distance from us, and, incredibly, even insights into the internal structure and equation of state of matter at densities far beyond anything we can replicate on Earth. We are literally probing the extreme physics of ultra-dense matter and gravity, all thanks to the tidal whispers carried on these space-time ripples. It's like listening to the universe's most brutal, elegant cosmic symphony, where the tidal forces are the lead instruments. But gravitational waves are only one part of our detective toolkit. We also rely heavily on electromagnetic observations, light in all its forms from radio waves to gamma rays, to spot those tidal fingerprints we discussed. Take thermal emissions, for instance. We know that tidal heating can generate immense internal heat within a celestial body, as seen with Io, Europa and Enceladus in our own solar system. This heat has to go somewhere, and much of it radiates outwards as infrared light. With powerful telescopes like the James Webb Space Telescope, JWST, we can now peer at exoplanets in unprecedented detail, searching for these thermal signatures. Imagine detecting a tidally locked exoplanet with a surprisingly warm night side, or an unusual heat distribution across its surface. This could be a direct clue that strong tidal forces are at play, generating internal friction and keeping the world geologically active. Such observations can help us infer a planet's internal composition, the presence of subsurface oceans, or even its potential for volcanic activity. It's like taking the temperature of a distant world to see if its internal engine is running hot, fueled by the relentless tug of its parent star or neighbouring planets. Beyond just heat, we look for direct geological activity. Remember Io, the solar system's most volcanically active body, constantly reshaped by Jupiter's tidal embrace? Or Enceladus, spewing geysers of water vapour into the space? These are spectacular spectacular tidal fingerprints. While directly observing exoplanet volcanoes or geysers is incredibly challenging with current technology, we're making progress. For example, spectroscopic analysis of an exoplanet's atmosphere could reveal the presence of volcanic gases like sulfur dioxide, suggesting active volcanism driven by tidal heating. Future generations of telescopes, perhaps those designed for direct imaging of exoplanets, might even be able to spot plumes or lava flows on distant worlds, providing undeniable evidence of tidal-driven geology. And then there are atmospheric signatures. On tidally locked exoplanets, where one side perpetually faces its star and the other is locked in the eternal night, tidal forces, combined with the extreme temperature gradient, drive powerful supersonic winds and exotic atmospheric circulation patterns. These can manifest as persistent hotspots that are offset from the substellar point, or as unique cloud formations and atmospheric chemical compositions. By analysing the light passing through or reflecting off an exoplanet's atmosphere, we can detect these complex dynamics and infer the powerful tidal forces shaping its weather and climate. We're essentially reading the atmospheric tea leaves of distant worlds, deciphering the story of their tidal interactions. Crucially, these detection methods aren't just about understanding planetary physics. They are profoundly intertwined with the search for life beyond Earth. Tidal forces, as we've seen, offer an alternative energy source for habitability, expanding our understanding of where life might thrive. The traditional Goldilocks zone around a star where temperatures allow for liquid water is a good starting point, but tidal heating pushes the boundaries. Subsurface oceans on moons like Europa and Enceladus, kept warm by tidal friction, are prime candidates for harbouring life even though they orbit far from the Sun. Detecting similar ocean worlds around other stars, perhaps through their thermal emissions or the spectroscopic signatures of their geysers, would be a monumental discovery. Moreover, tidal forces can drive geological cycling on a planet, a process often considered vital for sustaining long-term habitability. Plate tectonics on Earth, for example, helps regulate our planet's climate by cycling carbon dioxide, and it provides fresh nutrients to ecosystems. While direct plate tectonics on exoplanets is difficult to confirm, intense tidal heating could drive similar internal processes, leading to outgassing, volcanism, and a constantly renewed surface which could be crucial for the emergence and sustenance of life. The Terminator Zone worlds, with their stable twilight bands, could also be habitable havens, and detecting the signs of liquid water or a stable atmosphere in such a zone, perhaps through a combination of thermal and atmospheric observations, will be a game changer. Looking ahead, the future of tidal astronomy is incredibly exciting. We are on the cusp of a new era of discovery. Next-generation gravitational wave detectors, like the proposed space-based LISA, Laser Interferometer Space Antenna, or advanced ground-based observatories like the Einstein Telescope and Cosmic Explorer, will offer even greater sensitivity and a broader view of the gravitational wave sky. LISA, for instance, will be able to detect the gravitational waves from supermassive black hole mergers and the in-spiral of white dwarfs, further expanding our understanding of tidal forces in different cosmic contexts. On the electromagnetic front, future extremely large telescopes, ELTs, and advanced space telescopes will offer unprecedented resolution and light-gathering power, allowing us to characterize exoplanet atmospheres and surfaces with even greater detail. Imagine directly imaging the eyeball features of a tidally locked exoplanet or resolving the plumes erupting from a distant moon. These advancements will refine our understanding of how tidal interactions shape planetary evolution and habitability across the universe. Perhaps the most thrilling prospect is the rise of multi-messenger astronomy. This involves combining observations from different cosmic messengers, gravitational waves, electromagnetic radiation, neutrinos and cosmic rays, to paint a complete picture of extreme cosmic events. When LIGO first detected neutron star mergers, telescopes around the world immediately turned to the same patch of sky, observing the resulting cloniver explosion in gamma rays, X-rays, UV, visible light, infrared and radio waves. This simultaneous detection provided a wealth of information, confirming our theories about the creation of heavy elements and offering a holistic view of the tidal forces at play in these cataclysms. This integrated approach promises to unlock even more profound insights into the universe's most dynamic and enigmatic phenomena. So, as we bring our journey to a close, remember that the story of tidal forces is far from over. It's a living, breathing narrative of cosmic evolution, constantly being rewritten by new discoveries. From the subtle tug that keeps our moon's face perpetually turned towards us, to the gravitational maelstrom that tears stars apart around black holes. These forces are fundamental architects of the universe. They create and destroy, sculpt and shape, and in their elegant, brutal mechanics they reveal the deepest secrets of creation and the astonishing resilience of life itself. The universe is an intricate, awe-inspiring tapestry woven with the threads of gravity and motion. And tidal forces, these silent, powerful sculptors, are a testament to its profound complexity and endless wonder. They remind us that even the most seemingly simple observations like, why doesn't the moon spin, can lead us down a path of scientific discovery that spans the entire cosmos, challenging our assumptions and expanding our understanding of everything. The cosmic ballet continues, and we, the curious observers, continue to learn its mesmerizing steps. We've journeyed far, haven't we? From the familiar face of our moon to the fiery heart of distant exoplanets, and into the destructive embrace of black holes. We've seen how the subtle, differential tug of gravity, what we call tidal forces, leaves its indelible mark across the cosmos from the tiniest moonlet to the grandest galaxy. The detection of these tidal fingerprints, whether through the ripples of gravitational waves or the telltale glow of electromagnetic emissions, isn't just about identifying a phenomenon, it's about unveiling a universal architect. Think about it. Every story we've uncovered, every strange truth about cosmic motion circles back to this one fundamental principle. The moon does, but its peculiar tidally locked dance is a direct consequence of Earth's gravitational embrace. Io, perpetually flexed and heated, is a testament to Jupiter's immense tidal power, its volcanic fury a direct result of this cosmic massage. Europa and Enceladus, those icy bastions of potential life, harbour their subsurface oceans thanks to the same relentless internal churning. These aren't isolated incidents. They are chapters in a grand, interconnected narrative written by the invisible hand of tidal forces. This isn't merely a force of gentle persuasion either. We've witnessed its brutal elegance in the Roche limit, where celestial bodies are stretched and shredded into rings of stardust. We've peered into the abyss where black holes spaghettify stars, transforming magnificent suns into streams of incandescent plasma. And on the grandest scales imaginable, we have seen how tidal interactions between galaxies don't just shape their spiral arms, but orchestrate their mergers, forging new colossal structures from the remnants of the old. It's a force of creation and destruction, a sculptor and a wrecking ball, all rolled into one elegant, brutal cosmic mechanism. What truly unifies these disparate phenomena, this incredible range of effects from the subtle to the cataclysmic? It's the gradient of gravity, the idea that the gravitational pull isn't uniform across an object. This differential stress is what stretches, squishes, and ultimately shapes everything. It's why one side of the moon feels Earth's pull more strongly than the other, leading to those tidal bulges that Earth's gravity then drags, creating the torque that slowed the moon's spin. It's why Mercury's eccentric orbit combined with the Sun's tidal pull settled it into that unique 3-2 spin orbit resonance. Each instance, no matter how unique its manifestation, is a direct consequence of this fundamental principle at play. And what a principle it is! How this typ av storage, typ av it is. It challenges our intuitive understanding of the universe, doesn't it? We often imagine gravity as a simple pull, a force that keeps us on the ground or planets in orbit. But tidal forces reveal a far more nuanced and dynamic picture. They show us that gravity isn't just about attraction, it's about shaping. It's about evolution. It's about the relentless, grinding work of differential forces over billions of years, slowly but surely transforming worlds, stars, and even galaxies. This understanding is far from complete, of course. The universe, in its boundless complexity, always holds more secrets. But the insights we've gained into tidal forces are pushing the boundaries of scientific discovery in exciting new directions. What comes next in our quest to understand this unseen architect? The future, my friends, is bright with possibility. We are only just beginning to truly grasp the full implications of tidal forces. Next-generation gravitational wave observatories like the planned Laser Interferometer Space Antenna, LASER, promise to detect even more subtle ripples in space-time, allowing us to peer into the tidal dynamics of supermassive black hole mergers and the very early universe. Imagine the insights we'll gain into extreme gravity and the properties of matter under conditions we can only dream of recreating in a lab. LISA will be sensitive to gravitational waves from massive black hole binaries spiraling towards each other, a dance of cosmic titans where tidal distortions play a crucial role in their final moments, before they merge into an even larger black hole. These observations will not only test Einstein's theory of general relativity in extreme regimes, but also reveal the tidal imprints on the very fabric of space-time, offering direct evidence of these profound interactions on unprecedented scales. And when it comes to exoplanets, the search for tidal fingerprints is just accelerating. New telescopes, both ground-based and in space, are constantly refining our ability to characterize exoplanet atmospheres and surfaces. We're developing sophisticated models to predict how tidal heating might influence the habitability of worlds orbiting M-dwarf stars, especially those in the twilight zones of tidally locked planets. Could the subtle warmth from an internal tidal friction be the key to maintaining liquid water on an otherwise frozen exoplanet? Could it fuel subsurface hydrothermal vents, providing energy for alien life forms, much like on Europa or Enceladus? These are no longer just speculative questions. They are active areas of scientific inquiry, driving new missions and observational campaigns. Techniques like transit timing variations, TTVs, and radial velocity measurements, which detect the slight wobbles of stars caused by orbiting planets, are already hinting at complex multi-planet systems where tidal interactions can significantly alter orbits and internal heating. As our instruments become more precise, we might even directly observe the subtle deformation of exoplanets caused by tidal forces, like a tiny cosmic heartbeat, revealing their internal structure and composition in ways previously thought impossible. We're even exploring the intriguing possibility of rogue planets, worlds ejected from their star systems that might sustain internal heat and even subsurface oceans through tidal interactions with other passing rogue planets or even interstellar gas clouds. A truly mind-bending prospect for potential life in the interstellar void. Consider missions like Europa Clipper or the proposed Enceladus Orbilander. These probes aren't just looking for water, they're looking for signs of tidal heating in action, trying to understand the energy budget that sustains these potential oases. They're seeking evidence of plumes, of geological activity, of the very processes driven by the internal flexing caused by their giant planetary hosts. Every sniff of a potential biosignature, every measurement of heat flow, every image of a cracked ice shell brings us closer to understanding the role of tidal forces in the emergence and sustenance of life beyond Earth. Beyond individual celestial bodies, we're deepening our understanding of galactic evolution. Supercomputer simulations, now more powerful than ever, are allowing us to model the complex gravitational dance of interacting galaxies with unprecedented detail. We can literally watch in these digital universes how tidal forces stretch and pull, creating spectacular tidal tails and triggering bursts of star formation as gas clouds collide. These simulations help us interpret the stunning cosmic landscapes captured by telescopes like Hubble and the James Webb Space Telescope, revealing the elegant, brutal mechanics behind the universe's grandest structures. We're even using these models to trace the cosmic history of our own Milky Way, understanding how past tidal encounters with dwarf galaxies have shaped its current form and distribution of stars. So when we look up at the moon tonight, we no longer see just a silent companion. We see a testament to billions of years of gravitational interaction, a world shaped by the very forces we've explored. We see the elegant, brutal mechanics of the cosmos writ large. The question, why doesn't the moon spin, has led us down a rabbit hole of cosmic discovery, revealing a universe far more dynamic, interconnected, and profoundly strange than we could have ever imagined. This journey through tidal forces isn't just about physics, it's about perspective. It's about recognizing the intricate, often unseen connections that bind everything in the universe. It's about appreciating the profound cosmic ballet that has been unfolding for billions of years, a dance choreographed by gravity itself. Our solar system, our galaxy, and indeed the entire observable universe are active participants in this eternal gravitational tug-of-war, constantly being shaped, moulded, and transformed. It reminds us of the immense stretches of deep time over which these subtle forces accumulate, leading to monumental changes. What appears stable and eternal to our fleeting human lifespans is, on a cosmic scale, in constant flux, continuously being sculpted by these relentless, invisible hands. This realization fosters a profound humility, reminding us of our tiny yet privileged place in this grand cosmic drama. The moon's seemingly simple motion, its consistent face turned towards us, is a profound symbol of this cosmic truth. It's a daily reminder that nothing in the universe is truly static, that even the most familiar objects harbour deep, complex histories of interaction. It reminds us that appearances can be deceiving, and that beneath the surface of what seems obvious lies a fascinating world of scientific wonder waiting to be explored. It's a testament to the elegant simplicity of fundamental laws giving rise to astonishing complexity and beauty. As we conclude this exploration, remember that curiosity is our greatest tool. The questions we ask, however simple they may seem, often unlock the most profound answers. Why doesn't the moon spin was just the beginning. It opened the door to understanding how worlds are born, how they evolve, how they might harbour life, and how they ultimately meet their end. It showed us the universe not as a static collection of objects, but as a vibrant, ever-changing tapestry woven by the threads of gravity. We hope you've enjoyed this deep dive into the strange truth about the moon's motion and the incredible, pervasive power of tidal forces. If you found this journey as awe-inspiring as we did, drop a comment below and share your favourite tidal phenomenon. What aspect of the cosmic architecture fascinated you the most? And what other cosmic mysteries are you eager to unravel? The universe is vast, and there are always more questions to ask, more wonders to discover. Keep looking up, keep asking why, and keep exploring the unseen architects of the cosmos.